Welcome to the deep dive. So today we're tackling a really persistent problem in large language models, specifically that moment when they start to read too much and well, everything breaks down. We're looking at a new paper on Denoising Positional Encoding, or DoPE. It's a proposed fix for how models like Llama 3 handle these incredibly long sequences.
That's right. And for you, the mission here is to see how this work reframes a core part of the model. It looks at the attention map's positional encoding not as this perfect, clean signal, but as a noisy feature map. And the key insight, really, is that the solution is training-free. It's a method to detect and filter out that noise, and that's what unlocks these massive context windows, up to 64,000 tokens.
Okay, so before we get to the fix, we have to start with the foundation. Rotary Position Embedding, or RoE. And just to be clear for everyone listening, this isn't some obscure academic thing. RoE is the standard now, right? It's what's powering most of the big modern LLMs.
It is. It's incredibly effective because it encodes the relative positions of words by rotating the query and key vectors in the attention mechanism, and it works perfectly fine.
Within its comfort zone.
Within its training length, yes. The issue starts when you ask the model to process, say, 10 times more text than it's ever seen before. The performance just degrades. It's like it starts to forget what it read at the beginning, or it pays attention to the wrong things. That's the core limitation DoPE is trying to solve.
So what's actually failing? If RoPE is the engine, what's the specific part that breaks when you push it to 72K or even 64K tokens?
The research is really zeroed in on the cause. Pushing RoPE that far creates what they call outlier channels in the query and key parts of the model. So you can think of the positional encoding as using a bunch of different frequencies, almost like radio bands, to mark a token's position.
Okay.
What happens is a very small number of the low-frequency bands, their volume gets turned way, way up. They start to show these abnormally large A2 norms.
Okay, hold on. Let's translate that. Large A2 norms. What does that actually look like inside the model? What does that spike mean in practice?
It means a few specific parts of the position signal are just drowning everything else out. The SOE2 norm is just measuring that volume, and it confirms that a small piece of the representation has become totally dominant.
And this is where it becomes visible, right, in the attention matrix. These outliers are what create those bright band patterns that you see in visualizations of the model's attention.
Correct. That visual pattern is what's formally called the attention sink phenomenon. The model just gets stuck. It gives a massive amount of attention to the first few tokens, no matter what they are.
So it's like reading a 64,000-word book, but only ever thinking about the first paragraph.
That's a great way to put it. The theoretical reason is that over these huge new lengths, the low-frequency positional encodings align. They add up coherently, creating that massive norm spike, and the model just fixates on the start.
So to fix this, you can't just go in blind. You need a diagnostic tool to tell the good signal apart from this structural noise. And that's where DoPE brings in something called truncated matrix entropy.
This is the absolute core of the method. They use matrix entropy to measure the noise level in each attention head. A small entropy value, a small dollar, means the RoPE bands in that head have collapsed. They've become low rank.
So a small number means you've got a problem. You've got one of those noisy spikes.
Right. And a large matrix entropy means the opposite. It suggests the positional encoding is balanced and, well-behaved in that head.
But the paper makes a big deal about using truncated matrix entropy. Well, why the truncation? Why not just use the full entropy measure?
Because you don't care about all the noise, just the noise that's causing the problem. Truncated matrix entropy focuses only on the effective rank of the dominant part of the signal. It ignores all the little harmless background static. For those problem heads causing the attention sink, this truncated rank just collapses. It goes to almost 1.
So the tool isn't just looking for noise in general. It's surgically finding that one dominant failure, that single spike, and ignoring everything else.
Exactly. And that diagnosis lets them be very precise. A head with a small Hoare value is flagged as spiky and responsible for the attention sink.
I have to ask, though, couldn't you just use a simpler filter? If we know low frequencies are the problem, why not just cut them out instead of this whole entropy calculation?
That's a very good question. And the reason is that it's not just about frequency. It's about the structure of the head itself. What they found, and this is fascinating, is that the attention heads that are already good at extrapolation also have low-rank structures.
Wait, so the good heads are low rank too. How does that work?
It's a different type of low-rank structure. The crucial experiment was when they kept the positional encodings from these good low-rank heads and removed the encodings from the high-rank heads. Performance jumped by up to 10 points. It proves the truncated entropy is identifying a specific kind of low-rank structure that causes failure, which is different from the low-rank structure needed for good performance. And getting that kind of improvement without any retraining just validates the whole diagnostic approach.
The fact that it's training-free is huge. Okay, so we have a clear diagnosis. We know which heads are the culprits. What's the surgical strike? What are the 3 ways DoPE actually fixes the noise?
So DoPE gives you 3 different strategies, and you can sort of choose how aggressive you want to be.
Let's start with the first one, which sounds the most precise. DoPE by parts.
This one is very selective. It goes into a problem head and removes only the specific frequency bands linked to the low entropy. It uses a threshold based on the model's original training length to surgically snip out those coherent modes that cause the bright bands while leaving everything else intact.
So it's trimming the specific loud channels, not turning off the whole radio.
A good analogy. Then you have the second strategy, DoPE by all. It sounds less surgical, and it is.
How does that one work?
It's simpler. It applies a mask at the whole head level. If a head is identified as having that critical low rank, its entire positional encoding is just removed, zeroed out. So the bad heads lose all their positional information, and the good heads keep theirs.
Okay, and the final method, the one that seems the most interesting, is DoPE by Gaussian. You're replacing structure with random noise. How does that help?
It seems counterintuitive, I know, but it's a concept called stochastic regularization. For those noisy heads, instead of just deleting their positional encoding, you replace it with isotropic Gaussian noise. And this noise is carefully calibrated. Its variance matches the variance of the good RoP components that were kept.
So sometimes balanced random noise is better than structured but broken information.
It seems so. It's like hitting a reset button on that part of the model, restoring a kind of diversity where the structure had collapsed. And this method actually performed the best.
Which brings us to the test. They use the needle-in-a-haystack task,
Yeah.
which is notoriously difficult. Tell us about the experimental setup, especially the difference between the original and the noisy versions.
So, the standard needle-in-a-haystack task is just about finding one piece of information in a huge document. The noisy setup was much harder. They deliberately placed attention sync symbols tokens known to trigger this kind of bias right next to the needle. It's a way to create the exact conditions where RoP is known to fail. And they pushed the context all the way to 64K tokens.
So on that really tough, noisy 24K context, how much of a difference did DoPE make?
It was a very substantial improvement. The baseline model, dynamic NTK, scored around 75. With the best configuration, which was DoPE by Gaussian, that score jumped up to over 84. It's strong confirmation that you can counteract this positional noise even by modeling it with a careful distribution of new noise.
And the research also confirmed that the truncated entropy was a better predictor of failure than the full entropy, especially at those extreme lengths. Why was that?
Right. At the 64K context length, using truncated entropy with a rank of just $1 gave the best results. And remember, a rank 1 truncation is basically just looking at the single largest singular value of the matrix. It suggests that the longer the sequence gets, the more the failure is dominated by a single, incredibly sharp spike. The collapse is extremely localized.
And they had visual proof of this, connecting the metric to the actual attention patterns.
They did. The heads that the metric flagged as low entropy were exactly the ones producing the worst attention sync, visually fixating on the document's beginning. The other heads, the high entropy ones, were able to correctly spread their attention and find the needle. It's a very clear functional confirmation.
They also looked beyond just retrieval. It's something called many-shot in context learning, and found the model's reasoning ability also dropped off a cliff past 16K tokens.
Yes, and in that process, they found something really strange, something they called the cursive shortcut. They tried to make the task easier by putting examples of the answer directly into the context. Logically, that should have been a simple copy and paste shortcut for the model.
But it wasn't.
It made things worse. At 24K and 64K lengths, the model's performance actually dropped significantly when the answer was right there.
That's completely backwards. Why would giving it the answer hurt its performance?
Because long context isn't just about memory, it's about structural stability. Having that redundant shortcut information nearby actually seemed to overwhelm the flawed positional encoding system even more. It triggered the failure modes more aggressively. It proves these models don't just need more room, they need fundamentally better structural integrity.
So if we pull this all together, DoPE really offers a principled, parameter-free way to improve how these foundational models handle long sequences.
It does. It mitigates those low-rank artifacts that cause the attention sink, and it does it through this really rigorous surgical analysis using truncated matrix entropy. It's a clean method to retrofit existing models for huge context windows without the massive cost of retraining.
And as we close, there's one last fascinating thought from the analysis. It's about why the truncated entropy was so much more effective than the full metric. The research found that the heads it selected showed clear periodicity.
That's right, a repeating pattern along the sequence length axis. This seems to be the structural signature that the metric was isolating.
So the provocative thought for you to take away is that stability in these massive context windows might not come from having perfect, uniform position signals everywhere. It might depend more on finding and preserving these specific periodic geometric structures that maintain their integrity across vast distances.